Given a set of initial states and a goal state, we wish to compute a set of sequential solutions that will allow the Evo vehicle to reach the goal while satisfying the system dynamic constraints while minimizing the control effort and avoiding collisions. However, in a real scenario, a solution for this problem could be non-trivial given the implicit uncertainties from a dynamic environment that could increase the complexity of the problem. The initial conditions of the system can also include a type of uncertainty given by an initial distribution. Similarly, our system can be subject to disturbances and nonlinear dynamics that further increase the complexity of a solution. Therefore, as part of our solution, we propose a three-step process. First, we pre-compute an offline fixed control strategy that generates a reference trajectory P, such that the Evo vehicle can later use it with a tracking controller. Therefore, the resulting system dynamics only depend on an initial state and the trajectory P. On the second step, we estimate the state distribution at each time step. Lastly, on the third step, we optimize for P so that the goal is reached, the constraints are satisfied, and the collision probability and the control effort are minimized. Here, we can see the performance of our neural density predictor against the numerical approximation for the solution of the Liouville equation of the system dynamics. To evaluate the performance of our reference trajectory generator, we compared our method against two popular methods, a sampling-based method and a search-based method. We can see that our method generalizes the reference path with minimal control action when compared to the other two methods. To evaluate the performance of the density planner, we created a set of artificial environments with dynamic obstacles that move randomly. Additionally, we compare our method against a standard MPC implementation, a tube-based MPC, and an oracle method that is based on the optimal control formulation under perfect knowledge. Similarly, the standard MPC implementation does not consider any disturbances or model uncertainties. We can observe that the MPC methods can reach the solution. However, they can easily get stuck on local minima, while our method is able to tolerate more risk while minimizing the energy and time. Therefore, it can be seen that the density planner can reach the goal faster while maintaining safety. Additionally, we implemented our method on a real-life dataset recorded at German intersections. In this case, we added uncertainty to the vehicles by creating a normal distribution proportional to the obstacle size and the speed. In this case, a set of random origin-destination pairs are generated as the initial and goal states. On the left side, the uncertainty seen by the vehicle is depicted. Similarly, on the right side, a superposition of the actual environment is shown together with a safety region proportional to the uncertainty of the traffic vehicles. It can be seen that despite the uncertainties and the imperfect knowledge of the environment, our method is able to reach the destination faster than most of the other methods while maintaining its safety and avoiding getting stuck in deadlocks.